Hi, we're talking about notes for projectile motion for Ms. Sonheimer's physics class, Unit 5, projectile motion. So first off, in your notebook, you should have a new section called projectile motion. And at the front of this section, I would like you to start with notes. We're going to do notes over the entire chapter. So that way you are prepared and have the background knowledge, and then we'll work through each section. In smaller chunks throughout this semester or throughout this next week or so. First of all, set it up. Cornell notes, it should be projectile motion at the top. You should date it. It is not January 6th for you, but it is when I'm doing this video. Write vector and scalar quantities. For your 5.1, go through, utilize the textbook chapter 5 to set up or at least start your notes. What I would recommend before you list all your headers on the left is you read the textbook. So read the textbook and jot down about one or two items from each. Right? Do that for everything in this chapter. So review the textbook, read through it carefully, um, come up with a couple ideas. I'm reminding you in 5.2, this is where we bring up Pythagorean theorem again. Or I'm not even sure the book brings it up. They just kind of expect you to know it, which is why I taught it to you already. Um, so demonstrate where this is going to show up and go through for each section. Please ensure that you're leaving a little bit of room well, by the time you see this video, you should know that there should have been room to add additional commentary from the video. Okay, I haven't done this before, but I'm going to go ahead and just use their PowerPoint slideshow because they have really good videos that go along. Projectile motion described by horizontal and vertical components. This idea is going to be a big deal the rest of this chapter. So be aware that we are going to be breaking projectile motion into the horizontal and the vertical because each one depends on something different. So again, we talked about this in the last chapter where we were throwing a ball, where you were dropping things. This is now dealing with both the horizontal and the free fall component. We're combining them together. Okay. Quick review. I don't think I need to hit this too hard, but I'll talk about it briefly. Vector and scalar quantities. Vectors have magnitude and direction, while scalars only have a number. So examples include a vector would be velocity, acceleration, um, momentum, while a scalar is mass or time. So some examples of a scalar quantity and adding scalar quantities. There's no directional component. I have a bucket of sand and I add a kilogram of cement. The resulting mixture is 4 kilograms. I have 5 liters of water in a bucket. I pour it out. I pour out 5 liters of the 8 liters of water and only have 3 left. If I have a 60-minute trip, and then I get delayed. Somebody spent 15 minutes extra in the potty on the drive. It now takes 75 minutes. There's no direction component at all to this. Okay, how does scalar differ from vector? You guys know this. A vector has an arrow, it has a magnitude. This has an arrow to it. This is the key. This is really important. Once you add an arrow, you know it has some sort of direction. Okay, so we're going to go into velocity vectors. The objective here is at the end is to understand the resultant, how to get a resultant of two perpendicular vectors. Luckily, you already know how to do this, so this is review as well. So again, I reminded you about the arrow. Every vector arrow reflects on a number. So when you say 10 meters per second and you see 40 meters per second. This arrow, if it's going one direction, will be small, and this should be 4 times the arrow you drew here. So, because this was times 4 gets you to there. So please, 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 from here on out, ensure that your arrows represent the size that you are drawing. Here's a prime example. Here's an airplane, and on the left there is a tailwind. On the right there's a headwind. Notice each time the tailwind or the headwind is 20 kilometers an hour, and that ends up in a different resultant each time. The resultant is the sum of two vectors. Even if the sum is like subtracting, we're still like adding. See my quotes? We're still adding those arrows. So the first one, when you have a tailwind of 20 kilometers an hour and you're going 80, you're now moving at 100. But if you have a headwind of 20, you're now going at 60. Okay. So this reviews this. Remember, when they're opposite, you are actually going to end up subtracting. When it's a positive, you guys are going to add. When they're going the same direction, you add. Same as add, up and down, you subtract. That's what it's getting at here. Okay. Now, this is when we start looking at the perpendicular component. He's flying at 80 and he has a crosswind of 60. Okay, that's what it's reading. So when you read this question, this is when it says it's perpendicular, it's a right angle. Okay, so here's your sample. You draw your parallelogram rule. I did it, that's been done. And you draw your resultant. Now, you can calculate your resultant using the Pythagorean theorem. So that is a squared, a, this is technically, this is c, but in a rectangle, both this and this would be c. So this equidistance plus b squared equals c squared. You would plug in your numbers and solve for your resultant. I'm moving on from here. Okay, so suppose an airplane normally flying at 80 kilometers an hour encounters a wind at a right angle to its forward motion. While this will help the airplane fly a little bit faster, it will put it in a slightly different position, and it's going to have to account for this. Um, Another example that I like to use is when you're driving on the highway and here's your buddy in the fast lane and you're next to him and you're like, ha ha ha, we're going to race. Don't do that. I'm not recommending that you do that, but I know high school boys. Okay, so you're on the highway and you're driving. Well, then you get behind the slow dude. This guy's going super slow, and you have to get over. You have to change lanes to go around him to continue keeping up with your buddy in the fast lane. Okay, when you change lanes, you actually have to accelerate. You have to increase your velocity in order to maintain that same position. Because if you keep your foot just on the accelerator going that constant velocity and you change lanes, you're going to end up further behind right here just because you've expended energy to go to the right. So while in this case the plane is flying and it will increase the speed, it will blow it off course, of course. Same as your situation on the highway. Okay, what is the resultant of two perpendicular vectors? So the resultant is it's the final speed. Okay. Components of vectors. A perpendicular component of a vector. Each of them are independent. This is the hardest concept of this whole chapter, is that each component is independent. So any vector can be resolved into the two components. So if you know you're going this direction, you can use the parallelogram rule to determine the horizontal and vertical components of this object. So the two vectors that are right angles can add up to a given vector. And these are the components. So this is your resultant component. So in the process of doing this, the process of determining it is a resolution. So when you're resolving two components, that's the process of determining that vector. Okay, so they can be resolved. So if I have a ball being thrown up into the air, and we will be trying this eventually, you throw the ball into the air, there it goes. Whee! You can break it down into the horizontal component and the vertical component. Remember, the vertical component is going to deal with gravity. The horizontal component will be constant. Don't believe me? We are going to test this out with the video you made. Okay, so here's your vector, the vector that's been given, and then you can break it into the y component and the x component. Okay, horizontal component is just like horizontal ball rolling along a level surface without friction. It's constant. Sorry, I did lines for that. Vertical is affected by gravity. A projectile that moves through the air is acted on only, oh look, I just said that. So here we go. We're going to talk about a cannonball or a stone. We're going to talk about these. So a projectile is anything that's moving through the air that's only acted on by gravity and sometimes air resistance. Okay. So projectiles near the surface of the earth, these follow a curved path and these are called satellites. Wow, I spelled that wrong. Okay. They're called satellites, and I'm not going to spell it because I'm having a brain fart right now. Okay. Projectile motions can be separated into the horizontal component, which you noticed um, in our video analysis of the cart and the buggy, the fan cart and the buggy, that they moved at a constant rate across the floor. Okay. Now, you notice with basketball that it should have increased distance every time because gravity is affecting it. Okay? Each component is completely independent of each other. The downward motion is the same of that in free fall. So when you see this, I'm going to test this in class. When you launch a ball and drop a ball at the same time, they will follow the same motion and still hit the ground at the exact same time. Because once they're released from this position, the only thing acting on them is gravity. Okay? So gravity acts downward, both balls fall the same vertical distance from the top, and horizontally, the vertical distance has nothing to do with that free fall. So it doesn't matter how hard you throw it, it's still going to fall at 9.8 meters per second and hit the ground at the same time. Um, this motion is called a parabola. So this arc, that's a parabolic motion. When air resistance is small enough, um, all curved paths will be parabolic. Okay. Which can strike. So this should be, they both fall and hit the ground at the same time because once they're released from the cannon, they drop at the same time. Okay, I'm going to table this one because we ran out of time. We'll catch this one on the next one.